So last class we looked at, I want you guys to remember this formula for the rest of your code. I'm going to keep repeating it. So the formula is R double dot plus mu over R cubed is equal to. This defines the two-body problem. Okay. And mathematically, what kind of equation this is this? It's a It's a second order non-linear differential equation. Okay. And this defines, see what we have done is we've used physics and math to arrive at this problem state. Okay. So this is the two-body problem. Alright? And a solution, what would a solution entail? Now keep in mind what is constant and what is not constant here. So here you have to understand this R is equal to R of t. Okay. So your R dot will also be, you can say d over d square over dd square R of t. And mu is a constant. Okay. This R is simply again R. So this is the scalar, this is the vector. Now we have defined a two-body problem. Once we have defined the problem, in your engineering process, what do? What is your next step? You looked at an existing problem and you gave a mathematical output to that problem. And this is the mathematical output. So now you have to seek a mathematical solution. What is the solution? To the two-body problem. And this should be your next course. So what we'll do is we'll get to the solution. Now it so happens, what will that solution look like? Or what will that solution give you? What quantity will that solution? When you say solution, you need to find R of t. Okay? That's what your solution is. So if you have a differential equation, what do? If you seek a solution for, let's say if it's d square c or c double dot plus something, you'll find the solution will give you a value for that c. You remember? Yes. So now you have to find a solution for this R of t. Okay? So it so happens, and this is very important if you guys think about pursuing graduate studies, this is, there is no closed form calculus based solution to the above equation. Okay. So this is important actually. There is no closed form calculus based solution to the above problem. So if you try to solve this using your understanding of ordinary differential equations, you won't get a solution. Okay. So what we do is we seek a algebraic solution, and that's what we are going to do here. Okay. So to seek algebraic solution, we'll define. Everybody understands angular momentum?
Yeah.
What is angular momentum? What is momentum? Linear momentum? How is linear momentum defined?
Linear momentum is mass times velocity.
Mass times velocity, right? So similarly, you define angular momentum. You will define this h.
So angular momentum would be mass times angular velocity.
Something on those lines. This is r crossed with m2v. Okay? So here, what you say is, if you have, so we have been talking about this m1, right? And m2, right? And this m2 is orbiting around m1. You can say here, you can think of m2, and this is bigger particle is m1. So here h is the angular momentum of
1 relative to
2 relative to 1. Okay? So that is what, that is this h is m2, h21 is angular momentum of m2 with respect to m1. Okay. So keep in mind, we are always interested in this, the orbiting body, the angular momentum, the position, all the physical quantities we are describing, we are interested in the orbiting body, right? If we will always be here, the m1 is where our location will be in most cases, right? If you're looking at Earth, this is Earth. And what we want to know is, we want to know angular momentum of, let's say, the space station. This could be moon, this could be some small satellite you launch up in space. Okay, this is where you're going to be. So that's what you have to understand. Now we define this quantity h as specific angular momentum, okay, or angular momentum per unit mass. So So H in that case would be R cross V or R cross with R. Okay.
Which H are you referring to?
This H.
Oh.
This is the small h. Okay. So the specific angular momentum is small h. The complete angular momentum. See here, there is no mass quantity. This is the same as this, except that it is divided by mass. So that per unit mass. Per unit mass. Okay. So that is specific angular momentum. What do we know about angular momentum? What do you know about angular momentum or linear momentum? Anybody? Huh?
What do you know about angular?
What is known about angular momentum, linear momentum? What is known about energy? Anybody? Huh? It's conserved. Energy is conserved. Angular momentum is conserved. Linear momentum is conserved. Means it's constant. Okay. So if you take the derivative of a constant, what's going to happen? It will be 0. So that's what we'll do here. So think about this. You have, take this for example, okay? H is equal to R cross R dot, right? So d H over dt, what should this be equal to? Anybody? It should be 0, okay? And that's what we'll prove. That it's 0. So if you look at this, you have what is the cross product of this? How do you take the derivative of cross product? R cross with R double dot minus R dot cross with R dot. Okay. So keep in mind A cross B is derivative of A cross B is simply equal to A cross with B dot minus B cross with B dot. And this is also equal to, I have already given you this formula, plus B dot cross with B. Okay. So I've applied this formula here. Now this is equal to what? This is 0. Why is that 0?
Can't multiply by 2 by 2.
It's not multiply, it's cross product. Or what is the cross product definition? Cross product. See, that's it. This is where you when I asked you to do the review, the first homework, you should be aware. You cannot just give me something, write something and give it to me. This shows that you have not really paid attention to that review material. You understand? So cross product of the same vector is 0 because there is cross product involves what? Sign term. Okay. A cross A would be 0. Why? The angle between those two vectors, between the same vector is what? 0. So sine theta would be 0. So the vector cross product between the same two vectors is 0. So this is R cross with R dot. This is how we define dH over dt, right? Now, how do we show that this is 0? Look at this, okay? Recall r dot plus mu over r cube r is equal to 0. Okay. Recross above with r. Okay. Then we are going to get r cross with r double dot plus mu over r cube r cross with r is equal to 0. What is this again? The second term?
Which
This term is again 0. Why is that 0?
because they cross product or you cross on the same. Yeah.
Vector cross with itself is 0. That is what we did here. Vector cross with itself is 0. Vector cross, do you see vector cross with itself? R has been crossed with R, so it is 0.
But and it's attached to the new.
It doesn't matter, right? If this is 0, it doesn't matter what it is multiplied. Okay? So this is, if, as long as this is 0, it doesn't matter what it's like 0 multiplied by
Yeah, right. Okay.
0. Okay? So what you're going to get here is, again, this is also 0. So you're going to get R cross with R double dot is 0. Now compare these two. Are these two the same? R cross with R dot, R double dot, R cross with R double dot is equal to 0. So we can say this is equal to 0, which means H is a constant. Okay, or R cross with R dot is okay. So this you have to keep in mind. We have proved here that angular momentum is conserved. So specific angular momentum is conserved. What do you need to So such derivatives will be part of your exam. It's a very simple derivative. I'll say, starting with the two-body problem statement, prove that angular momentum is conserved. So where do you start? Starting with the two-body problem statement. Where is the two-body problem statement? Right. So you will start here, right? What will you do? Huh? You'll pre-cross it with R, okay? And then you'll show that this is 0, and you'll say this is nothing but this. You have to prove that, okay? So you can, if just this is equal to 0, that doesn't mean anything. You have to show that this is actually the derivative of the specific angular momentum. Just look at this figure for a minute. I want to show you this figure in. Alright. Focus on this figure. Alright. Can you guys see this? Yes.
Thank you.
So you see H is R cross V, right? Here. Everybody pay attention here. Don't take notes or be on your cell phone. Where is R? This is M. You guys understand this is M? M1. This is the small M2. This is the. So what is this body? This is the central body and this is called the orbiting body. Okay. So what is clear, Jerry? So this is going in this direction, okay? It's orbiting like this, counterclockwise. Right? This is that R. It's not the distance. What do you say that R is?
Radius.
No. Here if you see, huh?
The average displacement.
Position.
No, it's this R. What is this R?
Distance with respect to.
It's not the distance. When you say distance, what is distance? Is distance a scalar or a vector?
Relative position of orbiting body with respect to central body.
Relative position. So relative position and distance mean two things. Okay. So distance is what? Scalar or vector?
Scale.
Scalar. So that what you see there is that R they use a bold-faced letter to denote vector. Okay. So what is this R? If I say this, what is this R? You say relative position of the orbiting body with respect to the central body. So that the magnitude of this is the distance. Got it? So that's got it. So that we have the direction is also important for us. So distance could be from M1 to M2, M2 to M2 to M2, right? It doesn't matter. But the position vector is always from M1 to M2. If I say relative position of orbiting body with respect to the central body, it's always capital M1 to no cell phone. You cannot do cell phone. Okay.
R double dot acceleration.
R double dot is acceleration. Yes. So R double dot is acceleration of what?
The second.
The orbiting body. We are always interested in orbiting body. Remember that. We are not, the central body is where we are. Okay, that is our frame of reference. That is our reference body. Okay. Now, if you see, this is your R. This is the relative position or the position vector. And this is, what is this? That is a velocity vector. Okay. So when something is orbiting, this I want you guys to keep this in mind. The velocity vector is not tangential. Okay. What does that mean? What is tangential? Right. It's not tangential except at the unless I tell you it's tangential, it's not tangential. Okay. So there is there's a component which is tangential to this and a radial component of the velocity. You understand what I'm saying? So this velocity vector, I'll draw it here to make it a little more clear. We use this orbit rotation, okay? This is our orbit, right? Where would the central body be if this is an ellipse? Huh?
Foci.
The foci, right? So it will be either at this one of the focuses or one of the foci. It won't be here. Don't put the central body at the center. There's nothing at the center. Always remember, unless this is a circle. There's nothing at the center. Okay, it's always at one of the foci. So the central body is here. Okay, so this is, let's say, M1, and the orbiting body is, it's going like this. Got it? What is this vector? What is this? R. That's what is denoted there. And this would be the R dot. That R dot, do you see that R dot? Okay. So this vector will have this component. This is the radial component. Okay. This is the UR direction. And what is this direction? This is that U perpendicular tangential direction. Got it? Now think about this as the plane, the orbital plane. Got it? Orbital plane. The motion is always limited to a plane. Orbital motion is always limited to a plane. It doesn't come out of the plane anytime. Got it? That is what is being displayed there. And how we have to do that, how we have to understand that is, what is this H? How did we define H? R cross R dot, right? So if you take R crossed with this, where will that vector be? Perpendicular. It will be coming out of this. Okay? It will be like this. That vector will be like this. Right? Now if that vector is constant, that vector itself is constant, right? That is what it says. This angular momentum is conserved or constant. If this angular momentum has to be conserved, the motion has to be in this plane. It cannot come out of that plane. Right? If this is constant, this cannot change in direction or in length. It cannot change in direction. So, if this R was like this, if let's say R was like this, right? Then what would have happened?
It wouldn't be.
This would be like this. It won't be perpendicular. You get it? If it is out of plane, R or V dot, this R or V dot, if they come out of the plane.
So
this,
R dot and V is the same thing, right?
Yes.
Okay.
R dot and V is the same thing here. Okay, R dot is a velocity. So there is radial component. What is this radial component? This radial component is responsible for overcoming the acceleration due to gravity. Got it? So this there's actually what direction is the acceleration due to gravity acting? In the radial direction. Okay. So if the motion was tangential, what would have happened is it would spiral in actually. So this component addresses the acceleration due to gravity, the force due to acceleration due to gravity, and this keeps it in that motion, in that orbit. Okay. So now what you need to understand is, see that H dot, you understand this vector H dot or H cap? That H cap, H is again R crossed with R dot, and H cap is, what is this?
H over magnitude.
Magnitude. Okay. Now this R, you can say R, you can write R in like this. There are three, you can form a reference coordinate system here with this as the x-axis or UR direction, this as the y direction, and this as the z direction. Okay, so your R is only in UR direction, right? Everybody agrees?
You saying R, like, it's like X the direction, right?
Ah, right. It's only in that the radial direction. There is no tangential direction to R. Got it? But V is, there are two components for V, or R dot. There is a R dot component, I'll call this V, R, UR, plus V, perpendicular, U perpendicular. Does this make sense? Does this make sense? Let's do this video. Jayla, does this make sense?
Do we just take the,
So this is your V, okay? This is
B in
the X direction or R direction. The component of V in R direction. This is the component of V in the perpendicular direction.
Oh, R is the main. Okay, I get it.
R doesn't have a component in this direction because it is in that direction. Got it? V has component in that direction.
So it's like R dot, right?
R dot or that is V.
U R, okay.
So I'll just name it V.
Okay.
Simplification.
B, right. Right, okay.
Okay. So this makes sense? Everybody? Right? So now if I cross this, what will I do? R, VR, and UR crossed with UR plus R V perpendicular UR crossed with U perpendicular. What is this?
0.
This is again 0, right? Vector crossed with itself. And this is R V perpendicular. So this turns out to be R V perpendicular.
Cross.
What is this direction?
Which direction? Y.
UR crossed with U perpendicular.
Z.
Z or here what is this direction?
It's off the screen again.
Huh?
Is this perpendicular?
It's this H.
Oh, so Z.
No. The direction.
Oh, okay. Okay.
H itself is not 0. The derivative of H is 0.
Oh, okay.
So this H is, if you see, this is that direction. Here it is that H direction. You see it? So this is H. Okay. So your H can be written as this. Or you can say alternatively H is R V. What is the difference between this one and this one?
Unit vector.
No? What is the difference between this one? This is the,
that's a vector.
that's a vector. This is a
That's a scalar.
scalar. Got it? This is the magnitude of the vector H. What it means is only the tangential component of the velocity contributes to the angular momentum. Lost?
Can you repeat that?
Are you guys following or you guys are lost? How about you?
I'm lost.
But I didn't hear what you just said.
You understand angular velocity, angular momentum now, right?
Yes.
Everybody understands angular momentum. Everybody understands this step? You understand that, right? So what I've done is I've just created a coordinate system here. Okay, the coordinate system is, one is UR, the perpendicular to that is this U perpendicular, and there is another one which completes the third, which is in this direction. Okay, now my UR is in that direction. Velocity is this. Velocity has two components. Okay, this one and this one. This is the component in that direction. This is the component in the tangential direction. Right? You know how to resolve a vector. Now what I did is I take this and I distribute this. This cross this, which is this. This cross this, which is this. So this would be 0 because this vector is multiplied by this vector is vector crossed with itself is 0. This is vector crossed with it's here, this vector. So you have to remember x crossed with y is z. I told you this. Keep in mind this x, y, z. X crossed with y is z. Y crossed with z is x. And z crossed with x is y. So this has to be cyclic. You see x, y, z, cyclically I changed it. Cyclically means x went here, y and z shifted. Y, z, x. You cannot just rotate this. So cyclically again I shifted. Y went here, z and x shifted. Okay, so here this is that x direction. This is that y direction. This is the z.
And that's what we're trying to find, right?
You're not trying to find. What you're trying to prove here is the tangential component is the only component which contributes to the angular momentum. Okay. So this angular momentum, sometimes angular momentum will be expressed like this. You should not be surprised. Okay. So let's go back to our original discussion. What we wanted to prove was we wanted to find a solution, right, to the two-body problem. What we do is we start with what we call R plus mu over R2 R dU. So post cross with H. What that means is you just do R double dot cross with H is equal to H plus mu over Q R cross with H is equal to, just keep this as 0. So what I've done is, this is the two-body problem. We're trying to find a solution to the two-body problem. The first step is cross it with H.
I thought you crossed with R.
That's to get it to prove that H is 0.
So this is, yeah, H is not 0.
I mean, well, H, the derivative of H is 0.
Right, the derivative of H. So that is, so what we're trying to do is we're trying to prove angular momentum is conserved. Okay? So here if you see, this is the so here what you can do is you can write this as d over dt of r dot cross with h. Okay? Is equal to, what I'm going to do is just let's do this. Left hand side is equal to r double dot r cross with h can be written as h. Okay. Left hand side equal to this is the left hand side, this is the right hand side. So the left hand side can be written as this. Why can it be written like this?
Will you put equal sign?
Left hand side equal to, this is the left hand side, this can be written as this. Okay. If you take the derivative of this, what are you going to get?
You're gonna
R double dot crossed with
H
minus
R dot H dot.
what is H dot?
0.
0. The derivative of that is 0. So this can be written as this. Got it? Now, right hand side is equal to let's look at mu over R cube. I'll focus on this 1 over R cube R cross with H. Okay. We'll get the mu and minus sign in a bit. I'll just focus on this. Okay. So what can this be written as? This is what is H? H is?
What happened to the B?
I'll get it back into the equation. Let's just focus on this. Okay. So this is the right hand side, right? Forget about the minus mu for now. We'll get it into this. So this is what is H? R cross,
R dot. No, dot.
right? I'll just replace this with this. Now what is this?
Oh, that's 0. No. Oh. Wait, you crossing it? Then you crossing it? What is up?
Remember your vector triple product. Okay? This is A cross B cross C. So you have to use the back minus cap rule. Okay? So what you're going to do is back minus cap rule will give you. This is B A C, right? So it will be
R.
R.
A is R.
A is again R.
And cross C, which is R
Dot
dot.
is with
Oh, dot is R.
B A C.
R dot.
R dot. Okay. Minus C A B.
Okay. So C is the R dot.
R.
Cross dot R.
There's no cross. Okay. So when you're doing the back minus cap rule, the cross gets converted to this. There is no cross in the back minus cap. So this can be written as 1 over R cube. Now, I want you to prove something. A dot A is A dot. Okay. You will go and prove this as part of your assignment. I'll post the assignment today. Vector A dotted with its derivative is equal to scalar A multiplied by its scalar derivative. Okay. You have to prove this. I'll tell you how to prove this. I'll give you a hint and you have to do it as part of your assignment.
What is the assignment do?
Next week. So what we'll do is we'll apply that here. What you're going to get is R dot. We're going to apply that identity minus R dot R square.
Okay.
We'll stop here. I think you guys have to leave. See, I think before you guys leave, I think you're not prepared for classes. You're not prepared enough. Try to prepare whatever review material I've given to you. Go through that review material. again, because it seems like you're lost. These are all, you should be aware of cross product, the vector cross with itself, vector dotted with itself, and this was part of the review material. So most of you have just written what that review material is, but I want you to go through that again and again. Okay, vector identities, scalar identities. Otherwise, again, you get lost and it will become very difficult for you to follow. Okay, and there are lectures out there already existing. So you can, if you want to really prepare, go through those lectures and come here. Attendance, roll. Here, write it on this one. Just write the date.
Yeah. And you say old lectures are on?
Old lectures are already